So there's this infinite hotel. The rooms are numbered with the positive integers 1, 2, 3, 4, and all the way up, and it's full. And I go there and I tell the manager I want a room. He says we're full, but we'll shuffle around, see what we can do. And so he tells the person in room 1 to move into room 2, 2 into room 3, 3 into room 4, and so on. Because there's an infinite number of rooms, there's always an and so on. So I go into room 1. But now these guests are all here for a philatelist's conference, and that doesn't leave until Saturday, and an infinite set of geologists show up wanting rooms for their conference. And the manager says we're full, but we'll shuffle around. So again, he asked the person in room 1 to move into room 2. That only frees up one room, but then he asked the person in room 2 to move into room 4, in room 3 to room 6, so now 3 is freed up, and so on. And in general, the guest in room N moves into room 2N. The mth new guest gets put in room 2M minus 1. So we've settled this new set, this new infinite set of guests into the also infinite set of odd-numbered rooms, while moving the existing infinite set of guests into the infinite set of even-numbered rooms. So now these aliens that built the infinite hotel, they're nothing if not ambitious. They weren't content to build one infinite hotel. They decided to build an infinite number of infinite hotels. But they had to dismantle so many galaxies to do it that they got in trouble with the EPA, and they were ordered to dismantle all but one. So they did. The problem is they were all full, and now these guests need a place to stay. So we have M running from 1 all the way up, and N running from 1 all the way up. Right. Now I'll give you a second to pause the video and try to figure out a way to fit each guest into a different room of our one infinite hotel, and I'll give you a hint. Think of prime numbers and prime factorizations. Alright, pause. Back. Good. Alright, here's an easy way. Take the nth guest from the nth hotel and put them in room 2 raised to the n times 3 raised to the m. Since prime factorizations are unique, each unique ordered pair will go to a unique number. Now this is not very efficient. A very slick way to do this efficiently is to construct a table, putting the hotel number along the top and the guest number along the side, and then settling by squares: room 1, room 2, room 3, room 4, 5, 6, 7, 8, 9, and so on and so forth, ad infinitum. Now what does this have to do with our number system? Well, the initial infinite set of rooms is our counting numbers, or our natural numbers. Alright. When I show up, it's like we're adding 0 to this set. So what is variously called the positive integers, or the natural numbers union the singleton set 0. That set has the same cardinality. It's the same size because there's a one-to-one correspondence between this set and that set, even though this set has an element that this set does not have. They're the same size. Now when the infinite set of geologists show up, that's like adding all the negative numbers. The first new guest can be given the number -1, the second new guest -2, so we see that this set is still the same. Still the same size as our counting numbers. Well, what's really fun about this is that this table shows that the same is true for the set of all fractions. We can treat the hotel number as the numerator of a fraction and the guest number as a denominator of a fraction, and make a one-to-one well, not one-to-one correspondence, because some of these fractions are the same. 1/2 is the same as 2/4. But at least we have a one-to-many correspondence. We're putting the same fraction, the same quantity expressed as a fraction, into an infinite number of rooms. But all fractions get at least one room. So the set of fractions, called Q for quotients, is the set of all P over Q such that P and Q are elements of the natural numbers. Well, that's not exactly right. They should be elements of integers, but this can be extended to negative numbers as well. Just think of going around in a spiral. Okay, so all of these sets have the same size, and you might say, what of it? Infinity is infinity, and it's infinite, and why should we even imagine that different infinite things should be of different sizes? Well, let's assume for the moment that infinity is infinity. There is only one infinity, and consider the set of magnitudes. All right. Now, we have a good system for representing magnitudes. It's our decimal system. And each decimal number has some whole part, and then a decimal point, some fractional part. All right. So I'm just going to look at the fractional parts. So these are magnitudes between 0 and 1. Now, if infinity is infinity and it's always the same infinity, then we can call one of these magnitudes the first one, and another the second one, and so on. We can make a list of them because we're assuming that they have the same infinity as the counting numbers. So we can count them. That's what's called countable. So let's do that. The first one, I'm just going to call that A1, is point A11, A12, A13, and so on, where these are digits to the right-hand side of a decimal point. Any string of digits like this will create another magnitude. And the second one in a list, A2, point A21, A22, A23, and so on, and so on. So we have a complete list. We don't know which one is first, and so we're using A's instead of actual numbers. But once this list is constructed, and here it is, I'm going to go and make a new number, call it B. And the way I'm going to do this is I'm going to knock on door number 1 and ask, what's your first digit? And then whatever that is, I'll use that to construct my first digit in this way. B1 is equal to A11 plus 1 modulo 10, so a 9 rolls back around to 0. And in general, I'm going to knock on the nth door, ask the number, what's your nth digit, add 1 to that, and roll 9s around to a 0. Now, this number B is not the first number in our list because its first digit is different. It's not the second number on their list because the second digit is different, and likewise it cannot be the nth number on the list because the nth digit is different. So here's a contradiction. We assumed that this was a complete list, that it had every magnitude between 0 and 1. Here's a magnitude between 0 and 1 that is not on the list. A list cannot at the same time both have and not have all magnitudes between 0 and 1, so there's a contradiction. Therefore, our original assumption that this list was complete, that this list can even be made, is false. Now, if a list cannot be made of these magnitudes, and a list can be made of the natural numbers, they're of different sizes. There's no one-to-one correspondence. Okay, so maybe this is just an academic abstraction. Do these things even exist? Maybe maybe there's some error with our representation system here, with our decimal system, right? And that the only true magnitudes are fractions of integers, and everything else is just an abstraction. Well, I mean, numbers are abstractions, but maybe these are like contradictory abstractions that break our number system at some point. Well, let me give you a concrete example of one number that is magnitude and is not a fraction. So, to demonstrate the existence of this magnitude, I'm going to construct a square, side length 1, draw its diagonal. Now, by the Pythagorean theorem, this is the magnitude that, when squared, when multiplied by itself, gives 2. Excuse me. So let's assume that I'm wrong and that there is a fraction, p divided by q, which is equal to that magnitude. Now, if we have a fraction of integers, we can, in principle, cancel any common factors. Right? If these are both even, we can cancel a 2 out of both and get another p and q. If they have a 3 in common, cancel the 3's and get another p and q. So let's cancel all the common factors. Done. Well, let's square both sides. Well, this implies that p squared is the same as twice q squared. What do we call a number that has a factor of 2? An even number. Now, if p squared is even, that means it has a factor of 2, but it's also a number multiplied by itself. So any of those factors of 2 have to come from that number, and it gets it twice because it's squared. So p squared is a factor of 4, is a multiple of 4. Or in other words, p is equal to twice some number m, and p squared is 4m squared. So let's replace that up here. 4m squared is 2q squared. Well, canceling gives us 2m squared is q squared, which means q squared is an even number, which means q is an even number, which means it has a factor of 2, but up here we canceled all the common factors. There's a contradiction. We cannot have two numbers that both have and do not have common factors. And so our initial assumption that there is a fraction is wrong. So here's a number that is a magnitude, it's the diagonal of a unit square, that cannot be expressed as a fraction. Thank you.